Before going to Paley-Wiener criteria, we look at the filter characteristics of linear systems. So what did we say so far? So far we have talked about filters. What does the filter do? It modifies the characteristics of the frequencies in the input signals, right? That is what the filter does. Now, for a given system, if f of t is the input, my output is given by y of t, right? For any system with transfer function h of omega, my input signal f of t is nothing but the response y of input signal f of t, and my response is y of t. So the system processes the input signal in such a way that is characteristic of the system. That is nothing but f of t is processed in such a way that the system is defined or defined for, and it gives my response y of t. So what does this h of omega? If I take the input spectrum f of omega, and this is my h of omega, then my y is equals to f into h. This is by the convolution theorem of Fourier transform. Convolution theorem of Fourier transform, right? So this is my input spectrum, this is my system spectrum, and this is the response spectrum, right? Output spectrum. So if you look at this, h of omega acts as a weighing function to different frequencies in my input spectrum, right? F of omega into h of omega. If my f of omega is something like this, let me say, if my f of omega is something like this, and my h of omega is 0.5, let me say my h of omega is 0.5 and this is 1. So what happens? The magnitude is going to be multiplied by half, right? It is reduced. So how will my magnitude look like? It comes down to something like this, right? This is my y of omega, right? So what does it look like? H of omega acts as a weighing function to different frequencies. At this frequency, what is my f of omega? What is my h of omega? Both are multiplied to give my y of omega. So this is carried out for every frequency. This is carried out for every frequency in my output spectrum. So I can say h of omega acts as a weighing function to different frequencies. That is, the system acts as a kind of filter to various frequency components. It acts as a kind of filter to various frequency components. Suppose let me consider a low pass filter. Low pass filter, right? My input signal or input frequency, my f of omega, right? F of omega has frequencies from negative 200 to positive 200, or let me say it goes up to 400. It goes up to 400. These are the frequencies that are present in my f of omega. Negative 200 is there, positive 200 is there, positive 400 is also there. We are just assuming this is my input spectrum. Now I'll consider a low pass filter. I'll consider a low pass filter that has cutoff frequency at 300. That's cutoff frequency at 300 hertz or 300 radians per second, whichever it is. So what does this mean? From minus 300 to 300, my h of omega, this is my h of omega. How does it look like? It is a constant function. It is a constant function in this range. Outside this range, it is 0. So if I multiply these two, I should get my y of omega, right? Y is equals to h into f. So in f, what are the frequencies I have? I have an impulse at negative 200 and positive 200. So what is the value of h of omega at negative 200 and positive 200? It is 1. So I'll just multiply those impulses with 1. So this is my negative 200 impulse and this is my positive 200 impulse, and here positive 400 is multiplied with, here at 400 what is there, it is 0, so multiplied with 0. So this 400, the impulse at 400, frequency 400 is rejected by the filter. So this filter, this is the low pass filter. This system acts as a kind of filter to various frequency components. If you look at this, this acts as a filter to frequency components greater than 300. So all these components greater than 300 are filtered out, and other components are passed to the output. That is what this statement here tells us. The system modifies the spectral density function according to its filter characteristics. That is, according to the transfer function h of omega, which is the response of the system to various frequency components. The same thing we have discussed now. Now, during transmission through a system, when we are transmitting the input signal through a given system, some frequency components they can be increased in strength. Their strength can be boosted for some frequency components, while some can be attenuated. Right? If you are increasing the amplitude of certain frequency components, that means you are amplifying those frequency components, and if you are attenuating certain frequency components, that means you are rejecting those frequency components. Some remain unaffected. For some frequency components, you might actually not amplify or attenuate, you might just pass them as they are, right? You will just multiply them with 1. So there are 3 types of amplitude modifications that can be done through transmission through a system for any frequency component. One is boosting the signal, one attenuating the signal, and one there is no change in the signal amplitude or the signal amplitude of the frequency component. And each frequency component also suffers a different amount of phase shift. Right? Phase shift is a function of omega. Right? Phase shift is a function of omega. So based on omega, my phase shift keeps on varying. Based on the frequency, my phase shift varies. So each frequency component in the input signal suffers a different amount of phase shift, right? So this is what is the filter characteristics of linear systems. So now let us see an example of filter characteristic of linear system. So if you look at this is a RC filter. This is the RC circuit, right? RC circuit, and it's also called RC filter. This is the practical version of a low pass filter. This is a practical version of low pass filter. We'll see how. And so this is my system here. My system and my input. We'll look at what the output is going to be. So first I'll find the impulse response of my system. So to find the impulse response of the system, what should I find? I should find the transfer function first. So transfer function is nothing but output spectrum by input spectrum. Now what is my output spectrum? It is nothing but, if you remember, we have already discussed this. R must be replaced by R, C must be replaced by 1 by j omega C, and L by j omega L to find the transfer function. Now in place of C, now I'm going to have 1 by j omega C. Now my output loop consists of only the capacitor, right? So my output is going to be 1 by j omega C, and my input loop is going to consist of a series combination of resistor and capacitor, right? So that is going to be R plus j omega C, R plus 1 by j omega C. So this I'm going to simplify. So I'll take LCM of j omega C. It's going to be 1 plus j omega RC in the denominator and 1 by j omega C in the numerator. So my j omega c gets cancelled. So I'm left with 1 by j omega rc, right? Now to get this in the standard form, this is my h of omega. Now I'm trying to get this into the standard form to find my impulse response, right? So now what I'm going to do is I'm going to take RC common in the denominator, and what I have 1 by RC plus j omega. So this is nothing but 1 by RC is my constant, and 1 by j omega plus 1 by RC. So this is in the form of 1 by j omega plus A. 1 by j omega plus A. So now I'm going to find the impulse response. Now I'm going to find the impulse response. That is nothing but inverse Fourier transform of my h of omega. Inverse Fourier transform, right? Since 1 by RC is a constant, I'll get it outside. What is inverse Fourier transform of 1 by j omega plus A? It is e power minus at, e power minus at, e power minus at into u of t. This is 1 by RC, right? This is 1 by RC. Now in place of A I have 1 by RC. So 1 by RC into e power minus 1 by RC into t u of t. This is my impulse response. This is my impulse response. Now if I pass my input through this filter, what is the output I'm going to arrive at? What is the output I will obtain? That is what I have to see. So what is my input function? F of t is defined from 0 to t, and it is a constant 1 in this range. Now to find my response, it is nothing but convolution of the input with impulse response, right? Convolution of input with impulse response. So this is the formula for convolution, right? Now in place of h of tau, I'm going to substitute 1 by RC e power minus tau by RC into u of tau, and in place of f of t minus tau, I'm going to substitute 1, right? I'm going to substitute 1. Now h of tau has u of tau. u of tau u of tau is defined only for tau. It is only defined for tau greater than or equal to 0. And then my f of t minus tau, here in place of t, if I substitute t minus tau, it is less than or equal to t. It is less than or equal to t. So what is the value of tau? Tau is greater than or equal to t minus capital T. T minus capital T. So the lower limit now for minus infinite to infinite, I have my limits. Now I can change my lower limit to t minus tau. Tau is greater than or equal to 0, and tau is greater than or equal to t minus capital T. So I can change my lower limit to t minus capital T. And now I will integrate it and substitute my limits. So if I integrate and substitute my limits, this is my final response, right? This is the response I'm getting. Y of t is equal to e power minus t minus capital T divided by RC. So let me draw the response y of t, right? Let me draw the response y of t. So this is t, and this is my y of t, my response. This is 0, right? Now this is my t. When my t, capital T, sorry, when my small t is between 0 and capital T, right? Small t is between 0 and capital T. So what happens? T minus capital T. What will this become? T is less than capital T. What is this going to be? This is going to be a negative number. This is going to be a negative number. So a negative number multiplied by a negative number. What is it going to be? It is going to be a positive number. So e power some positive number. That is a rising exponential. That is a rising exponential, right? I can write it as a rising exponential, right? I can write it as a rising exponential. When it's almost equal to t, what happens? When it is very close to t, what happens? The difference between t and t is very less. That means t is almost equal to capital T. T minus t becomes 0. E power 0 becomes 1. So when it comes close to t, my response is going to be equal to 1, 1. And when small t is greater than capital T, then t minus capital T is a positive number. Positive into a negative sign, I have a negative number. So e power negative is a decaying exponential. So it slowly starts to decay. It slowly starts to decay. So this is my response. Let me draw it a little more clearly so you will understand it. It slowly rises. It slowly rises and it steadies at 1. It steadies itself at 1 and then it slowly starts to decay. And it slowly starts to decay. This is my response. So what if you look at the input and the output, what we can infer is there is a sudden rise in the input. This sudden rise means the frequency that is present at this position is high frequency. Sudden rise indicates high frequency components. Sudden rise indicates high frequency components. Sudden drop also indicates high frequency components. Right? This is the no change constant. That means low frequency component. Right? So whenever there is a sudden rise, my capacitor can't charge to its complete value instantly. So it's going to charge slowly. It's going to charge slowly. So this is the charge of the capacitor, that is charging up of the capacitor. So when it reaches its maximum, it is going to hold that value. It's going to hold that value. And when there's a sudden drop, I'm going to discharge. My capacitor is going to discharge. Now it can't discharge from 1 to 0 immediately. It is going to take some time. It's going to take some time. That is this exponential decay. That is exponential decay. So if you look at that, there's a high frequency here and there's a high frequency here. So these two high frequencies are rejected in my output. I have a slowly increasing exponential here. That is a lower frequency, right? This high frequency is rejected. So, and this high frequency is also rejected, right? So this is nothing but it is rejecting the high frequency signals and passing through the low frequency signal. It is passing the low frequency signal, right? It is passing the low frequency signal and it is rejecting the high frequency signal. Hence, this is nothing but my system is nothing but a low pass filter. My system is nothing but a low pass filter. And if you look at my impulse response, it is multiplied by u of t. My impulse response is multiplied by u of t. That means it is going to be present only for values of t greater than 0. Only for values of t greater than 0, it will be defined. That is e power minus 1 by RC into t, right? This is my h of t. This is the exponential decay signal, e power minus t by RC, right? And at this point, it's going to be 1 by RC. That is my maximum amplitude. So this is my impulse response. That is, it is only defined for the positive values of t. And for negative values of t, it is 0. Which means my system is causal. My system is causal. My impulse response is causal and my system is also causal, which means my system can be practically realizable or physically realizable, right? So that is why we call this as practical low pass filter. That is why we call this as a practical low pass filter. Right?